Hi everyone and Assalamualaikum. This is part 2 for chapter 3, pressure drop in part 9. So I hope you remain happy and stay calm and stay at home just like me here. I'm so happy. Okay, so pressure drops. Okay, what is actually pressure drop? So we understand pressure drop um, is the difference in total pressure between 2 points of a fluid flow in a line. So that is pressure drop. So is it good or not, this pressure drop? Okay, so the excessive pressure drop in a system will lead to the low system performance and excessive energy consumptions. Okay, so that's why every equipment, every pipeline, we having the acceptable range of pressure drop. So when we do the calculations of the design of the equipment, we need to fulfill certain range of pressure drop. That's why. Okay, that's the reason because we want to save the energy consumptions. Okay, go back to this pressure drop in pipeline. Okay, pressure drop in pipeline happen due to the frictions. Okay, so due to the frictions and is a function of fluid flow rates. Okay, then fluid density, viscosity, the pipe diameter, and also pipe surface roughness, and also the length of the pipe. So you can see here, this one is the equations for the pressure drop in pipeline. Okay, friction factor is dependent on the Reynolds numbers and pipe roughness. And later on we can see the friction factors can be found in figure 5.11, which is this figure. Okay, so in this figure, okay, we need to do is to find the Reynolds numbers, okay, of the fluid, the flow in that pipe, and then we have the pipe roughness here. Okay, so this line all pipe roughness, and this the line the bottom here is for the smooth pipe. So each of the pipe roughness values here got values. Okay, so we check Reynolds numbers, check pipe roughness, then we can get what is the frictions, which is F here. Okay, so looking back to these equations, okay, so this equation is to calculate the pressure drop in Newton per meter square. So we can see here you have friction factors. These friction factors that we can find in the figures 5.11. Okay, then we have pipe length. Okay, then pipe inside diameter, fluid density, so fluid velocity. So as I mentioned that this pressure drop happen in pipeline due to frictions, and then it's a function of fluid flow rates, okay, fluid density, viscosity, pipe diameter, pipe surface roughness, and length of the pipe. Okay, so absolute surface roughness are commonly used pipe as in this table. Okay, this one is a common material and this one is the absolute roughness. Okay, so later in the equations we need to use the relative roughness. So how to calculate relative roughness is the absolute roughness divided by the pipe inside diameter that we use. Okay, so this one is the figures 5.11 for us to find the friction factors. Okay, these equations, okay, is it same with the previous equation? Yes, it's same with the previous equations. Okay, this equation and data in figure 5.11 only valid for constant fluid viscosity and density, which is Newtonian fluids. Okay, for non-Newtonian fluids, which is the viscosity is a function of shear stress, more complex methods are needed to determine the pressure drop. Okay, so in here we only will cover Newtonian fluid, which is the viscosity and the density is constant. Okay, for a gas flow through a pipe, so the gas density is a function of pressure. This equation and data in 5.11 can be used to estimate the pressure drop, but it may be need to divide the pipeline into the short sections and sum the results. So it might be not accurate to use directly the figure 5.11, so means we only can estimate the pressure drop if for the gas flow. Okay, any obstructions to flow will generate turbulence and cause a pressure drop. So if you look at the picture here, this one is example of pipe fittings. You have coupling, cap, reducer, T, plug, screw cross, strip elbow, 90-degree, okay, long nipples, return band, reducer, T, 45-degree elbow. So all of this is the pipe fittings, okay. And also in pipeline also we're going to have valve, okay. We can have globe valve, gate valve, and so on. Okay, all of these pipe fittings and valve will contribute to the additional pressure drop, okay, in the pipeline. Okay, so later on in the calculations we also need to consider these fittings and the valve used in the pipeline. Okay, this table showing the pressure loss in pipe fitting and valve. So you have fitting of valve in the list here, and all these the values for K, which is number of velocity head. Later you will use this in the calculations. And the next column here is number of equivalent pipe diameter. Okay, so this one is the list. Okay, so we can have two methods to estimate the miscellaneous pressure losses in the pipeline. Okay, methods number one. Okay, as the number of velocity heads lost at each fitting of valve. So if you see the list here have K number of velocity head, so we are going to use that values later. Then what we need to do is total number of velocity head loss due to all fittings and valve need to plus together with pressure drop due to pipe friction. So this is how we calculate using the first methods. Okay, for the second methods, as a length of pipe that will cause the same pressure loss as the fitting of valve. So here what we do is total number of equivalent pipe diameter times the diameter of the pipe being used, then what we get is length of pipe. Later on need to add to the actual together with the actual pipe length. So once we have the example later, you understand these two methods. Okay, let's go to the example. So example 5.1, this one is from the textbook. A pipeline connecting two tanks contains 4 standard elbows. So remember all of these fittings, okay, and the valve. So have 4 standard elbows. A globe valve that is fully open. This is important, okay, important information. The globe valve is fully open, and then the gate valve is half open. So the line is commercial steel pipe. So important points here, 25 millimeter internal diameter with the length is 120 meter. So this one is the physical properties, okay, of the fluid. Viscosity 0.99 millinewton meter power negative 2 second. Then the density 998 kilogram per meter cubic. So the question is asked us to calculate the total pressure drop due to the frictions when the flow rate is 3,500 kilogram per hour. So remember we have these two methods, okay, to estimate the pressure losses, the total pressure losses. Okay, so these two is to calculate or to estimate miscellaneous pressure losses because of fitting and the valve used in the pipeline. Okay, go back to this. So the solutions. First, we need to find the cross-sectional area of the pipe, as usual, using this pi over 4 d power of 2. Then what we get is 0.491 times 10 minus 3 meter square. Okay, so that's the cross-sectional area. So remember, we use we make sure the unit is consistent. This one is millimeter, then we convert to meter, so it becomes meter square. Then we calculate the fluid velocity. Okay, since it's given to us the flow rates. Okay, so these are the fluids velocity, 3500 kilogram per hour. So we just convert this to become in meter per second. Okay, this one is 3,600 second, and these values, okay, is the cross-sectional area of the pipe, and this one is the density. Then later what we get is 1.98 meter per second. Then we calculate the Renault numbers. Renault is rho u d over mu, the viscosity. And please take note that this one is 0.99 milli, okay, millinewton meter negative 2s. So just convert this one to Newton. No, this one is milli, okay, times 10 negative 3. So what we get here, the Renault numbers, to make sure the Renault numbers no units, is dimensionless number. So what we get here is 49,900, okay, round out to 5 times 10 power 4. Okay, so the pipe that we're using here is, as mentioned here, the line is commercial steel pipe. Okay, so commercial steel pipe. So we refer to table 5.2. Go and find table 5.2. Where is it? Okay, this is the table 5.2. Commercial steel pipe. The absolute roughness is 0.046. Okay, so we just write here 0.046 millimeter. So the relative roughness is the absolute roughness divided by the inside diameter, inner diameter of the pipe. So we get 0.0018, we can round out to 0.002. So now time to find the friction factors. Okay, so look at the chart from figure 5.11. Since like this part is so small, so okay, so what's the value of relative roughness? 0.002. So first look at the Renault numbers. Okay, as per calculator, Renault numbers is 5 times 10 power 4. Okay, so 5 times 4 is around here. Then we look at the pipe roughness. Okay, where is it? Okay, it's somewhere here. Okay, 0.002, they go up, so it's here, this point, and then just go to find the f. Okay, so what we get here, the f is 0.0032. Okay, so now we need to make a list, okay, based on the problem statements, is based on the questions. Okay, so this one is the miscellaneous losses. So this one is the list of fitting and valve they're going to use, okay, in the pipeline. So you need to remember that when we have equipments, of course they have entry point and also the exit point of the pipeline. Okay, so this one have entry point. Okay, so we look at this table 5.3. okay, we need to check and find the value of K and also equivalence part diameter. Okay, so for N3, okay, we look at the list. Okay, so N3 is, okay, sharp reductions. Okay, 0.5, 25, and then look at elbows. Okay, since like it's not mentioned in what degree the elbow, we go to the standard elbow, radius elbow here. Okay, we take 0.8 times 4 because we have 4 elbows. Okay, so 40 times 4 because we have 4 elbows, and then the globe valve here is open. Okay, we check globe valve. Okay, fully open, which is 6 and also 300. Just write again. You get valve half opens, okay, 4 and 200. So exit, okay, sudden expansions, okay, 150. Okay, so we just total up all of these values, so we get the total number of velocity hits and also this equivalence by diameter. So using the first methods, velocity hits. So velocity head, we need to use these equations to calculate what is the velocity head. Okay, is 0.20 meter of the liquid. Okay, then the head loss is 0.2 times 14.7. Okay, so where you get it? This 14.7 is the number of velocity head. Okay, So head loss is 0.2 times 114.7, you get 2.94 meter. Okay, so as a pressure values, this one because in meter, so we convert into Newton per meter square. Okay, so 2.94 meter, 998 is the density, this one is the velocity, 9.8 kg. Okay, so we get 28,754. So later we calculate the friction loss in the pipe. Okay, so this is the friction loss of the pipe. This one is the miscellaneous losses. Okay, so this one is quite direct. Friction loss in pipe, just substitute all the informations, all the values of F, L, the length 120 meter, DI inside diameter 25 times 10 negative 3 meters, and then rho, okay, rho 988, U velocity 1.98 divided by 2, then we get 250 kilonewton here. Okay, 250,388 newton meter square. So this friction loss in pipe, okay, plus with these miscellaneous losses, then we get the total pressure, which is 270 kilonewton per meter square. That one is method number 1. So now go to method number 2, equivalent pipe diameter. So extra length of pipe to allow for miscellaneous losses. Okay, 735. Where you get this 735? 735 is based on this miscellaneous losses table that we have. Get the value from table 513 and calculate the total equivalent pipe diameter. So 735. So 735 times the inside diameter of the pipe, so we get 18.4 meter. So the total length for the pressure drop 120. What is 120? Check again. 120. What is 120? 120 meter is the length of the pipe, okay, of the commercial strip pipe that we are using here. Okay, so this one is the total length of the pipe you are using, the exact pipe. This one 18.4 meter is the miscellaneous losses, okay, that is equivalent to the pipe length. Okay, 18.4, so what we get is 138.4 meter. Okay, so what you can do here is just directly use these equations. Okay, the pressure drop in the pipeline, okay, just substitute what is the friction factors, okay, and this L, okay, we are not substitute 120, but we substitute the total length for the pressure drop calculations here. 18.4 include the miscellaneous losses here, then this will be 138.4, and the rest will be the same inside diameter, and then density, velocity divided by 2, what you get is 277 kilonewton meter square. So you can see here there's not so much difference here, 270 and also 277 kilonewton meter square. Okay, the two methods will not give exactly the same results. The method using the velocity heads is the more fundamentally correct approach. Okay, but the use of equivalence diameter is easier to apply and sufficiently accurate for use in the preliminary design calculation. Means method 2, okay, is suitable to be used in the preliminary design calculations, but to get the more accurate, okay, means to get the more accurate pressure drop calculations, the method number 1 is more correct approach. Okay, I think that's all. Thank you. See you for the next part.